As is our tradition, when we introduce a random variable, we also talk about how we can find characteristics. So you are familiar with expected values. I'm going to show you how to find the expected value for a joint probability mass function. And then we're going to look at covariance and correlation, which are two statistics that become relevant when you have two random variables. So if you recall, when you had one random variable, if you wanted to find the expected value of some function in terms of x, hx, then this is how you did it. Remember, we're only focusing on the discrete case, so it's a summation, not an integral. Now, the bivariate case, which is what we're interested in this situation, is going to look like this. So you're going to have some function that is a function of x and y, and then you're going to find that product in there, hxy, pxy. So it's similar to that, but just include your y. And then since you have two values, you have your x and your y, you have the double summation now. Let's do an example. I think that's probably the best way to really understand how this works. Suppose an instructor is given a short quiz and it has two parts. X is the number of points earned in the first part. Y is the number of points earned in the second part. Suppose this table gives you the joint probability mass function of x and y. So what this tells us is y can only take on values 0, 5, or 10. And for x, that's actually your part 1 of the test, you can only get 0 or 5. And then this table gives you the probabilities for the different combinations of x and y scores. You've been asked to find the expected value of the total number of points earned in the two parts. So in other words, the total number is x plus y, but you want the expected value of that. So we're going to apply this definition in the next slide so you can see how it works. So in place of hxy, we've been given x plus y. So all I've done is I've gone and substituted it there as well. So you have x plus y times pxy. And remember, this summation is over all the possibilities of x and y. Just like in the univariate case, you sum over all the possibilities. So you need to make sure you get every single x and y pair and substitute it in there and just keep doing the summation. So the first case here, you have 0, 0. So I've done here, I've put 0 in place of x, 0 in place of y in both of these terms. The next one is 0, 5. So you do the same thing, 0, 5, 0, 5. All the way to the end, you have x is equal to 5, y is equal to 10. I've done the same thing here. X is 5, y is 10. Same thing there. X is 5, y is 10. So it's just the same thing over and over again. Now you just go sum in your P00. Look for it in the table. P00 is 0.3. And P05 is 0.15, and you end up going throughout the whole table. So 0 plus 0 gives you 0, times P00 of 0.3 obviously gives you 0. And you do the same thing all the way to the end. 5 plus 10 gives you 15, so that's the first term. And then P510 is 0.3, so that's that second term there. And if you plug this into your calculator, you should get 8.76 is your final answer. In the textbook, they do a similar example. They use the absolute value in a very interesting question, but it's the same procedure, so don't be intimidated. Whatever you have here, so regardless of what function it is, you always treat it the same way. So I have these interesting cases for you to try. It's the same question, just find these expected values. Don't be intimidated by what's inside. It's just the same procedure. Follow exactly what I did and you will get the correct answers. Let's have a look at what's called covariance. So suppose I propose this question. Do taller persons make better basketball players? Obviously that is debatable, but it's actually the same as asking, is there a relationship between height and skill, basketball skill? So you would have a way of measuring basketball skill as well. And the question is there a relationship? Or in other words, are they dependent or not? And you'll find that, let's say you have x and y, so one could be the height and this could be the scale. You would say they are dependent if you find that x increases as y changes or x decreases as y changes. So in other words, you can see a clear pattern in what's happening in one variable as you change or vary the other one. So we have measures of dependency. So we have the covariance and the correlation. And I'm going to show you in the next slide how to calculate it. So all along we checked, are variables dependent or not? And what we're going to do now is we're going to put a measure of that dependency. So if you have two random variables, x and y, and you know that they're not independent, you want to put a certain value to say how strong is this relationship. So you use what's called the covariance. So this is just the expected value of x minus mu x, y minus mu y. So this is almost similar to the questions you did earlier. What's inside here is your hxy function. So you're just going to apply this, and if you just apply this definition, then it follows directly that this is how you'd calculate it. So just note here, this is your shorthand notation to say covariance. So it's just cov, C-O-V for covariance, and then x, y. And this is the function. So usually we're not going to ask you to calculate it directly using this because it's quite a bit of work. But there is a shortcut formula, just like in the univariate case, and I'm going to show you that in a couple of slides. So for now, let's have a look at the impact of whatever the relationship is on x and y on the covariance. In practice, if you had two variables which you are interested in, what you would start by doing, which is good practice, is to plot it in a graph, something like this. So on the x-axis, you would plot the x values, and then the y value, you'd put the corresponding. So this is an example of the kind of data that you would get. And you can immediately see from this graph that the data follows an upward trend. And I can tell you straight away that this covariance is positive. So what that means actually, before we look at the definition, is that large values of x tend to occur with large values of y. So let's take this point for instance. It's a large value. It lies on this upper part of the x-axis. And if you go across, it also lies on the upper part of the y-axis. And it's the same for the values in this region. And if you go down to the lower end, you see that these are small x values. They tend to occur with other small y values. So you also have the case like this. Now, if we look at the definition, we can immediately see why we have a positive covariance. So let's start off by looking at values in this quadrant here. Remember, this formula is x minus its mean, y minus its mean. Okay, so these are the univariate means, as you know from chapter 3. So if you take, let's say, this point once again, if you go down immediately, you can see that it's greater than its mean. So this difference is going to be positive. And then if you take the y value, the difference between that y and its mean is also going to be positive because they are greater than their means. So you end up with a product of two positive things, and this probability is always positive. So ultimately, this summation ends up being the sum of positive things whenever it's in this region here, greater than the means. So you have positive values, great. Now, how about the values on this side? Now, on this side, I can tell you that it's negative from both cases. So if you focus on this point, if you go down here, you can see it's less than its mean. And if you go across, you see the y value is also less than its mean. So you end up with this product being a negative value times a negative value. And ultimately, so regardless if the values are there or there, you always end up multiplying the same signs, which gives you positive values that you're summing over. So that's why your covariance is greater than 0 whenever you have data like this. Now, in the case where covariance is negative, you see almost the opposite. The data is sloping downwards. So instead of sloping like this, immediately you can see that the data looks like this. It lies sort of along a straight line. It's sloping downwards, therefore the covariance is going to be negative. So you'll see that large values of x tend to occur with small values of y, and vice versa. Small values of y tend to occur with large values of y. So we can focus on any example. Let's take this one. You can see the x value is going to be large, but the y value is below its mean. So that's actually the first case. And then the case where you have a small x value, so let's look at this one. If you go here, it's small, but then the value of y tends to be large now. So immediately you can see just from the graph. So once again, you're going to see that you tend to get negative values in this summation, and that's why you have a negative covariance. So you focus on this point. This value is greater than its mean on the x-axis, but it's less than its mean on the y-axis. So if you take the products on those two parts, you'll have negative and positive. And you have the same thing going on in this quadrant here. If you have, let's say, this value, you can see that y is greater than its mean, but x is less than its mean. So if you find that difference, you're going to have different signs once again. And remember, positive times negative or vice versa gives you a negative value. So you end up summing a lot of negative values, which gives you a negative covariance. Now lastly, suppose there's no clear pattern, you're going to find that the covariance is going to be near 0. So they need to be clear upward or downward, sort of along a straight line. Okay, I'll tell you more about this straight line idea a little bit later. So if you look at that formula, remember values in this quadrant and that quadrant tended to give you positive, positive or negative, negative. Values in this quadrant and that quadrant tended to give you negative, positive, and vice versa. So in these values, you start getting a bunch of negative sums and things in that summation. These ones give you positive ones. And ultimately what happens is that the positive ones tend to cancel out with the negative ones, and that's how you end up with a covariance near 0. So in your textbook, they give you this example where they've used the definition to calculate the covariance. So mu x is just the mean of x, the way you know it from chapter 3. So it's xpx. So you use the marginal distribution to find this 175. Mu y, you also use the marginal distribution in the same way, and you get 125. So if you plug x minus 175, y minus 125, this is what you get. So you just need to evaluate this for every possibility of x and y. So that's 100 and 0, 100 and 100, and so on. So x will be 100, y is 0, and then x 100, 0 is 0.2. So you do this for all 6 of these different ones, and you get that. But like I said earlier, we're not going to use this formula most of the time. We're going to use a shortcut. So let's have a look at that. In the univariate case, the shortcut formula for sigma squared was just this formula, which you're familiar with. Now in the bivariate case, the shortcut formula for the covariance looks like this. You have expected value of x, y minus the mean of x and the mean of y. Just a note, you will find that if you find the covariance of x and x, you end up with expected value of x squared, which is that, and you end up with the mean of x squared, which is exactly the same formula as this one. So the covariance on the same variable is just the same as the variance. So let us do an example. This is what you can expect to be asked to do. So we already did exercises where you found this. This is from chapter 3, so we can just go straight into it. So remember, according to that expected value function of your hxy, we did this example like this already. You just take all the possibilities for x and y, and then you just plug them in the relevant places. You can verify this for yourself, but you get 23,750. Now remember, in the univariate case, it was just x times px. Remember, px is just the marginal distribution of x, or it's the same distribution you had in chapter 3. So it's just this one. So you'll take all the x values and multiply by the corresponding probabilities. So 100 times p100, 250 times p250, and ultimately you get 175. Now you follow the same procedure to get the expected value of y, because you need that there. Same as you did in chapter 3. Now to get the covariance, you just take the expected value of xy, which you got there, and then the product of these means, 175 and 125, and this is the final answer that you get. And you'll notice that this is the exact same answer that we got when we used the long formula, and that's what you expected. So now we're probably thinking, great, we can measure the relationship, or rather the extent of the dependence between two variables. But there is a problem with covariance. Covariance is affected by the units of measurement. So for example, if I found the covariance between two things that are in centimeters, and then if I converted those values to, let's say, meters, if I calculate the covariance, I would get a completely different value. Like, the covariance isn't bounded. It can take absolutely any value from minus infinity to infinity. So it doesn't provide a very good measure. You can't compare covariances. It's not a standard the way it is. And ideally, we don't want units to have an effect on the measure of the strength of that relationship. So what we do is we scale the covariance. And in scaling it, we end up with a new statistic, which we call correlation. So you end up with your correlation coefficient. What you do is you take the covariance that you've calculated, and then you divide it by the standard deviation of x and the standard deviation of y. And immediately what this does, it scales it. Now you have this measure. This Greek letter is called rho, R-H-O. So if you hear me say rho, I'm referring to the correlation coefficient. It's just this term here. Now, rho is now scaled, because I can tell you immediately rho lies between -1 and 1. So you're not going to get different values. So if I calculated rho on my data in centimeters and rho on my data in meters, I will get the same value. So let's look at an example of how we'd calculate the covariance. So it's as follows. So this is the previous example we did. We found the covariance was 1,875, and then we've already found the expected values as 175 and 125. So this is another way you can look at the formula. So you take the variances and then you square everything. And remember, this just gives you the standard deviation because you put the square root over each term. So it's exactly the same as what I showed you just now. So now to find the variance of x, or any univariate case, this is the formula. That's the shortcut formula you already know. So you do it the same way as always. So if you start off now with the expected value of x squared, because we already have this part from there, you're just going to use the definition, which is the sum of x squared px. So you focus on the univariate distribution now. And if you work out everything, that is 100 squared times 0.5 plus 250 squared times 0.5. This is the answer that you should get. So you can verify that. So ultimately, if you plug it into that formula, you'll get 36250 minus 175 squared, which should give you 5,625. Follow the same procedure to get the variance of y. Now, if you just plug it straight into this definition, which is something you need to memorize and know, then the variance just goes in the denominator there, and this is what you end up with. And the answer is 0.301. So let's have a look at how you interpret this value now. So you know it's between -1 and 1, but therefore, So now, in order to interpret the meaning of that row, you're going to check which interval it is, and then you make a conclusion based on that. So in summary, you can rewrite this like this. Okay, so suppose you have a correlation coefficient in this interval, then you're going to say that you have a weak linear relationship. If you have it in this interval, minus 0.8 to minus 0.5, or this interval, then immediately you can say that there is a moderate linear relationship. If you find that your value lies in there or in there, then you have a strong linear relationship. If you get a correlation value equal to 0, so it's perfectly in the middle, then you can say that there is no linear relationship. So that's just a special note. Keep that in mind, and we'll get to that just now. So let's go back to our example. We had 0.3 as our correlation coefficient, so it lies somewhere here. So if I asked you to interpret that, this is what you would say. You would say that the variables have a weak positive linear relationship. So it's in the weak region, and remember it was a positive value, it was 0.3. So that's where I got the sign from. And I said it's a weak positive linear relationship. So those are important parts. Weak, positive, linear. So we like to divide the marks like that. Make sure you have those three things. Now I've emphasized linear because that is actually very important. We are actually only measuring linear relationship. And let me explain to you what I mean by that in the next slide. So you have these two random variables, x and y, and if you plot them on this line, these are the values. So I actually generated this data from y equal to 2x. Okay, so you know mathematically these values lie perfectly on a straight line. So if you calculate the correlation coefficient, you'd actually find that it's equal to 1. Now, how about this case? Now, your data isn't lying on a straight line, but there is a relationship. Okay, this data, it's not random. You can see there is a clear pattern. So there's definitely something going on between x and y. But if you calculate the correlation coefficient, you find that it's equal to 0. So that brings me to my point. We say that the correlation coefficient measures a linear relationship. It doesn't measure other kinds of relationships. So if you get a correlation coefficient equal to 0, don't say that there is no relationship. That's not true. In this case especially, sometimes there actually is another relationship. It's just not linear. So what you should say is that the correlation, it is equal to 0, which means that there is no linear relationship, but there may be some other relationship in your data. So that's what I mean when I keep emphasizing that we're only measuring the relationship with respect to a straight line. Does your data lie on a straight line or not, and to what extent? So as I told you earlier, the correlation coefficient lies between minus 1 and 1 after that scaling. You will only get correlation equal to 1, which is the strongest positive linear relationship when your data lies perfectly on a straight line sloping upwards. Okay. And you'll get a negative minus 1 when you also have a perfect negative linear relationship. So that means your data lies perfectly on a straight line and it's sloping downwards. So that's the second part of the first proposition on page 250. The other proposition is pretty much what I've actually just said right now. So you can just take a moment to read exactly what it says here. This is all from the textbook. I just wanted to highlight it to you. Now let's have a look at what does this all mean in terms of your data graphically. So remember in the previous case, we looked at what does it mean if your covariance is less than 0, 0, or greater than 0, and we associated with these three different scenarios. Yeah. What if we take the correlation coefficient now? How is this going to affect the correlation coefficient? So immediately, you know the formula is just scaled version of the covariance. So you're just dividing by the standard deviation of x and y. But the standard deviation of y is always going to be positive. We're going to trust that it's not going to be equal to 0. We're not going to give you anything where it's equal to 0. Otherwise, this doesn't work. But in the case where it is positive, it's never going to be negative. If you take whatever sign's up there and you divide by a positive value, then you end up keeping whatever that sign was. So in essence, what that means is if the covariance was negative, the correlation coefficient is always going to be negative also. And if the covariance was near 0, then the correlation coefficient is also going to be approximately 0. Similarly, in the last case, that's what you're going to have. So immediately you can tell the signs of your correlation coefficient by just looking at the trend in your data. So this leads me to the last example that I'd like you to do. This is exercise 26 on page 252 of the textbook. So you just see how that goes. Now, before we round off, I just want to touch on a few points that are relevant. So this is part 1 of the first proposition on page 250, and this is part 2. So let's focus on this first one first. Now, what this tells you is that the correlation coefficient is not affected by a linear change in the units of measurement. So what that means is if you found the correlation between x and y, and then you scaled x and y, so this is like you can see it's a line still, ax plus b, cy plus d. So all of it's a linear transformation on both of these. If you find the correlation on these, it's going to be exactly as a correlation on the original data before you even did the transformation. Now, this other proposition is now telling you, okay, what is the impact of this on independence and vice versa? So it's important to remember this. If x and y are independent, then the correlation coefficient is going to be equal to 0. Okay, but now let's look at the converse. What if the correlation coefficient is equal to 0? This does not imply independence. Okay, so that means even if you calculate a correlation coefficient and you get it equal to 0, don't you dare say that they are independent, because it doesn't hold in this direction. Independence implies rho is equal to 0, but rho equal to 0 does not imply independence. So you can actually verify this with an example. Suppose you have these two random variables, y1 and y2. We can see that they are not independent because you can just take any example you like, but you see that if you check the probability at 0, 0, it's not equal to 0, 0. So these are clearly dependent. But if you calculated the correlation coefficient in this example, you can work it out, you will find that it's equal to 0. So this immediately shows you that getting correlation equal to 0 doesn't mean that they're independent. This is a clear example where they are dependent. Now, just my final words. This is something interesting that you just need to understand as well. When you say that you have a relationship between two variables, it doesn't mean that one causes the other to happen. So that's what I mean when I say correlation does not imply causation. Just because x and y have a linear relationship, no matter how strong, it doesn't mean that y causes x or vice versa. This is summarized in this paragraph on page 151. You can read this, you can pause the video, have a look at it, and I'm just going to add another example on top of this to give you an idea of why this is the case. So let's take this example. If we have households that have coffee machines, you would probably actually find that they also tended to have healthy babies. So what that means to you is there is definitely a relationship between having a coffee machine and having a healthy baby. But just using common sense, does it make sense that if you had a coffee machine, does that mean you're going to have a healthy child? Like, that just doesn't even make much sense. So even though you will find that you will get some positive correlation, most likely in this case, you can't say one thing causes the other. There could be another underlying relationship between these two. So it's not that the coffee machine makes the baby healthy, but it's probably that families that are richer or more well off will probably have a coffee machine at home. So that means they can afford better health care for their babies. Therefore, they will have healthier babies. So the cause is not the coffee machine. The cause is something else underneath. But both these things are related to that cause. So never ever say that because there's a correlation, it caused the other thing to happen. Now that leads me to the end, and I hope you've enjoyed this, and I wish you all the best. Take care.